So this clip is some notes about the three-dimensional shapes of molecules. And we'll be looking at a system, a theory if you would, called VSEPR. So we'll start out with a definition. VSEPR stands for valence shell, so the valence electrons, electron pair, P is for pair, and then the last one is repulsion. So here's the idea. The idea is that electron pairs repel each other. Electrons can stand being in pairs, as in the lone pairs that are around the atoms, or the electrons that are paired up to form a bond. They can stand being next to each other, but the pairs themselves are repulsive to each other. And this ends up giving us a beautiful picture of the 5 different shapes. So the 5 main shapes. And to show these, I'm going to need some pipe cleaners. We'll start out, for example, with CH4. So CH4 is known as methane, and if you look at the Lewis dot structure, it looks like a cross. Carbon in the middle is the singleton, 4 hydrogens around. Each carbon has its 8 valence electrons, the hydrogens have 2. And I'd like to represent this with these 2 pipe cleaners by putting them together, wrapping around so they're stable. So if you put the pipe cleaners like that, that's about what the Lewis structure is. But this is flat. This is 2-dimensional. Really, molecules live in 3-dimensional space. The valence shell electron pair repulsion theory says that all of these bonds would be repelling each other and repelling each other equally. So they would end up orienting themselves so that they're equidistant from each other. So you end up with a molecule that's got this shape here. It's got, if I bend this right, all of the bonds are the same exact distance from the other. And if I turn it right, if I bend these right, they're about the same distance, and in nature they'd be exactly the same distance apart. This shape is called a tetrahedron. And to draw it, as if you've got balls and sticks, it would look something like that. So the first shape is a tetrahedron, and all of the angles are identical. The second shape I'm going to use as an example, NH3. Now this is ammonia, and if you make the Lewis structure for it, you've got the singleton ammonias in the middle, the hydrogens all around, and it needs a lone pair for nitrogen to have its stable octet. To show that with this structure, I'm going to take one of these legs from the tetrahedron and just wind it down. So now that wound down one represents the lone pair. But it still has some height to it. It's like a pyramid there, and this is fun because you can make it bounce. So we've got another shape, and this one has a really long name. It starts out with the word trigonal because there's 3 hydrogens around the central nitrogen. But since it's got this pyramid sort of height to it, it's called trigonal pyramidal. Trigonal pyramidal. And to draw the shape as if it's a ball and stick, you can go like that. But as long as you know what really that looks like, you've got it. And it's because this lone pair on top pushes down the hydrogens down there, pushes down the electrons that are doing the bonding. So it's got this 3-dimensional shape. The third shape, we'll use water as an example. Now the Lewis structure for water has oxygen in the middle, hydrogens on either side, and 2 lone pairs for the oxygen. So now oxygen has its 8 valence electrons. Each hydrogen has 2 like it needs. So to show that, we'll take the other, one of the other legs on our trigonal pyramidal guy and wind it down and end up with 2 lone pairs that are pushing down the bonded hydrogens. And this shape they call bent, which I think is apologizing for how long trigonal pyramidal is. So the bent shape of water is what makes life on Earth possible. Probably know that. So we've got a nice easy word, bent. The fourth one, for this one we're going to take BH3, boron trihydride, and this is one of the exceptions to the rules of the octet rule. Boron is stable with 6 valence electrons. So the Lewis structure for this one is just boron with its 6 valence electrons from the bonded hydrogens. So it doesn't have a lone pair. And to represent that with the pipe cleaners, unroll, straighten out the 2 that you rolled down, and yeah, now they're all bent, kind of crookedy, and then wrap those together to form one bond. So now the center is like the boron, and the hydrogens are on all 3 sides. And to make these all equidistant from each other, because they're repelling each other equally, you end up with, some people call it the Mercedes-Benz sign, not a peace sign. So get it all equidistant. Looks like that. The name of this shape, it's another trigonal. Just like we had trigonal pyramidal up there, this one, since there's 3 hydrogens around, is another trigonal. But it doesn't have any height to it. It's flat. Even in the best 3-dimensional world, it's still flat, kind of like a shuriken. So they call it trigonal, well, I would call it trigonal flat, but they call it trigonal planar, which is the geometry word for flat. And to draw it in the ball and stick model, you get like that. And these all have really nice 120-degree angles between them. So these should be the same. I didn't draw it perfectly. And then the last shape, for the last shape we'll use as an example carbon dioxide. Now when you do the Lewis structure for it, carbon needs to double bond with each one of the oxygens, which means that now they all have 8 valence electrons, but carbon does not have any lone pairs in the middle. So there's nothing pushing on the bonds, just like was nothing pushing on these bonds. So it ends up being flat or straight, just like that. So to show that, take the pipe cleaners and wrap them around like that, and you get a line or a stick. And I would call this stick if it were me, but the name that they have is linear. So carbon dioxide is a linear molecule, and it's because there's nothing to do the repelling of those double bonds there. Now there's one other example, which is actually much more common, and that's just any molecule that has 2 atoms. A 2-atom molecule, because there's no choice, it has to be linear. So for example, hydrogen chloride, HCl, is going to be linear. F2, fluorine gas, will be linear. Any molecule that has just 2 atoms is going to be linear as well, even if it's got triple bonds, like nitrogen. And those are the 5 shapes for the valence shell electron pair repulsion theory.